All right, so I'm going to get started. I know not the entire class is here yet, but I cannot wait for the whole class to be here to get started because we have a lot of stuff to cover in the entire semester. I hope you guys had a chance to take a look at the syllabus, okay? Read the syllabus and also watch the syllabus video because when I talk about the syllabus, I also explain why certain policies are there. So, do we have any questions about the syllabus? No questions? Okay. All right. So, if there are no questions about the syllabus, I do want to make sure that people understand that the lecture is being recorded. Only the voice is being recorded. I don't have a camera facing you for sure, and there's no camera facing me either. So whatever is on the projection screen is being recorded. My voice is being recorded, and if you ask questions, loud enough, that will be recorded as well. So that's just letting you guys know that we do have recordings.
Use this to put on your other door.
You can.
Well,
Yes,
people
go
keep
ahead.
going to your other door, so that's
Yeah, I couldn't unlock the other door. I
okay.
could unlock this one, so I know how to unlock a door. But either way, I could not make it so that you can open from the outside with that door.
Oh, okay.
Yeah.
Okay.
So that's
I'll put
probably
it
a
aside.
maintenance issue.
Okay.
Yep. Thank you. All right. So there's that. So without any questions about the syllabus, I assume that you guys have read about the absence policy, as well as academic integrity policy, as along with other things. So once I make that assumption, I will continue with the actual course content. But I'm going to assume that some people may not have read the syllabus. So I'm your instructor for CISP 310. The prerequisite of this class is CISP 360. So that means, when I check the prerequisite requirement for people who have not met the requirement and they do not file a petition form to challenge the prerequisite by the due date of this particular homework assignment, then I will start dropping people. So the prerequisite check is right here. If you check your own grade and you receive 1 out of 1 for this critical assignment, you're fine. There's no work that you need to do. On the other hand, if you see a blank or a zero, that means you need to somehow figure out how to show me that you have met the prerequisite of CISP 310. Do we have any questions about the prerequisite requirements? Okay, so for the most part, okay, if you took CISP 360 and passed it with a letter grade of C or better, somewhere within Los Rios, you'll be fine. It is mostly for people who come from outside the Los Rios district that they have to file a petition form to challenge the prerequisite. All right, so starting next week, we'll probably be joined by a few people from Sac State. That's usually what happens because at Sac State, apparently they do not offer enough classes of certain types of curriculum, so we end up with some of those students here as well. All right, so with all of that stuff done, I will continue to move down here. I have a few links here. One is to talk about how to take notes because I remember in past semesters, now remember I only teach CISP 310 and 440, and I have seen in multiple occasions people walk in with a cell phone and they be doing this during the entire class, and then they go like this occasionally, snap a picture, and then go back to this. Now, that's all I can say because I have no idea what they're doing on the phone. Maybe they're trying to take notes on the phone. That's entirely possible. But I cannot take notes with on my phone because I'm not so good at thumb typing, so it would not be a very efficient way for me to take notes. Um, Whatever you see on the screen is being recorded already, so there's no need to do your own recording of the screen. Uh, what you can do instead is to just kind of jot down the time of a screenshot that you go like, oh, that's probably going to be useful later on because this way you can go back to the video recording, which is going to be on YouTube, and just go to that time and then take whatever snapshot and do whatever you want with that screenshot on your own computer. Are we doing okay so far? All right. So taking notes is important. Okay, I know you're already in what the third class or the second class in the sequence of your computer science, and most of you know how to take notes already. But it doesn't hurt to kind of re-emphasize why taking notes is important. It is important to different people for different reasons. For myself, when I was in college, taking notes is only a way for me to continue to pay attention, to focus on the class material. Because when you listen to something, you look at the screen, the teacher talked about something, and you're trying to reformulate and write it down in your own words, you have to pay attention. Okay, it's not easy to do that just by as one of the tasks as you multitask. Okay, so I'm gonna go to Amazon and shop for this. I'm chatting with this person, and also I'm taking notes at the same time. I find that to be almost impossible. That may just be me. Okay, though some people may be able to do it, but I cannot pull that off. One of my friends, okay, who works at Lawrence Livermore National Lab, and I think his IQ beats mine by at least 10 or 20 points. Okay, so he took notes for a different reason. He had to take notes because he has dyslexia. So he had to read all the material ahead of time because verbal stuff to him is really difficult to understand because he keeps flipping the orders of the words and whatnot. So he had to read ahead of time, take notes during the class, and then he had to restudy the notes after class as well. Whereas I just took notes in class to stay focused in the class. I seldom had to read my own notes again. So that's for taking notes. And then this one, if anyone has click on it. It's about a journey of how I start to understand quantum computing. But at the same time, I document the thought process. Things that I do. Okay, how do I keep track of what I have learned so far, and how do I get back up? Because I had to drill all the way down because there was a lot of things that I did not know because I never took those math classes. So I had to drill really down, like go to Wikipedia, click on the link, go to another Wikipedia page, click another link, go to another Wikipedia page, click another link. So it was like 4 or 5 levels down. So by the time I understood that concept, it's like, but why was I here? So I had a way to go back up. I had to keep track of the map of the concepts so I can go back up and then I can relate that concept to other things that I needed to understand. So this link here is going to a article, some writing of mine that talks about that particular process. I will actually show you this, you know, quickly because I want to show people how to read it. It's like, what do you mean by how to read it? If you are interested in actual quantum mechanics and quantum computing, you can read the entire thing. On the other hand, you go like, but I'm taking 15 units, I don't have time to, take on something that I don't really need to know. That's fine. Read the boxes. Okay, the boxes do not contain anything specific to quantum computing. Instead, they are just describing general approaches of how I study and how I understand new concepts. So the boxes are really easy to understand, really easy to read, and they will give you some instructions. Well, I shouldn't say instructions. It will tell you how I do things. Now, does it work for you? Maybe, maybe not. Okay, but it shows you how I do things, and hopefully it might help certain people in this class. Not everybody, but hopefully some people will find it useful. So these are all general stuff. At the very end, I usually have something, but I'm not sure whether I still have those or not. All right. So at the end, we have personality assessment. Myers-Briggs type indicator is one of those. Okay. Yes, it is not scientific. Psychologists will say, nah, that stuff is not scientific. Probably not, but it will still give you an idea of how you operate. Okay. What works for me may not work for you. I talked about this a little bit yesterday, so if you're coming from CISP 440 from yesterday, this might be a repetition. Um, so when I take a class, I don't ask questions at all. If I don't understand something, I would just tell myself, I can't figure this out. Okay? So I'll just spend time to work on it. I don't ask people, so what does that mean? Or how do I do? Nope. I just figure that out by myself. And this is back in an era where there's no internet. There's no Google, there's no search engine, there's no AI. It's just me, the textbook, and my brain. Okay? And I can tell you it's an investment. Nobody is born super smart. I mean, there are a few people, but they're very, very small percentage. People get to be quote unquote smart or intelligent because of practice. So the the more time you spend to try to solve a problem by yourself, the more you're practicing how to reason and how to work things out by yourself, and then the more prepared you are by the time you graduate from a 4-year university and looking for work, because that is what they're looking for. They're not just looking at your GPA. For the most part, I don't think they pay that much attention to GPA anymore. Why do you think that is the case? Why do you think the pandemic had something to do with that? What happened during the pandemic? I mean, you guys all experienced the pandemic. So what happened?
Online classes.
Online classes. Okay, so what about online classes? I mean, we have been doing online classes since the 2010s. We moved the STEM courses online as well. That was the big change. So before we had psychology classes, English writing classes, that were online. They have been online for 10, 15 years before the pandemic. But the pandemic forced math, computer science, physics, chemistry, all of those courses to be online as well. So what do you think they found? They found that more people are relying on the internet and resources that they're not supposed to be using in online exams, otherwise known as cheating. Okay? So, how do you think they found that out? The STEM people found that out because they can process the result. It's like, how can we have an unusual cluster compared to when I taught this class on the ground or in person? People kind of cluster in a very different way. It's a bimodal distribution where you have a lot of people totally failing the class because those people just did not care. And then you have a bunch of people all the way over here, with really, really good grades instead of the usual bell curve. They look at the answers. It's like when they're wrong exactly the same way. With multiple choice questions, it's like they're not just getting it wrong, which is not unusual, but they all pick the same wrong answer. Hmm. So do you think employers would notice this sort of thing? They did. Okay? Short answer is they did. They look at those people who come in with a really high GPA from even good universities. And then they found that these people could not get the job done. It's like, what? It doesn't happen before the pandemic. I mean, this is like after the pandemic, this is suddenly happening. So what do you think as an employer, okay, as a hiring manager, you're working for a large company, what would you do when you find this kind of trend? Okay.
Harder.
Hmm?
You make it harder.
How do you make things harder? Well, it's not so much harder as it is you want to really make sure that people know their stuff when you hire those people. But how do you do that? You cannot do a Vulcan mind meld and actually know what they know, right? So what do you know? What do you do to check whether your new coming potential employees really know that stuff or not? You're the manager, okay? You want to hire the best people, but the GPA really doesn't tell you anything anymore. So what do? You give them a, yeah, go ahead.
Oh, I was gonna say, you do like a practical interview for skills, or you look at like past projects that they've
Yeah.
done.
Yeah, and that's why. What is the name of that website? Lead Code. That's why Lead Code took off because Google, Facebook, Pixar, they were all trying to give practical quote unquote exams to their interviewees. It's like, okay, on paper everything looks great. We would like to hire you, but before we do, please solve these problems in front of a panel, or they keep an eye on how people solve the problems. So they look at the actual performance of people. They give their incoming interviewees exams. And those exams are not coming from textbooks. They are all dynamic. They change them all the time because they know that people just kind of pass these things around, and so other people can just quote unquote study for interviews. So these employers know all of that already. So they keep making new ways to assess incoming employees, potential employees, to make sure that they know their stuff. Okay, so I will just let you guys know about the facts. Okay, what you want to do about it is up to you. Okay, so I can try my best, to prepare you guys for your interviews, for the situations that you will be in when you are employed. Obviously, this does not apply to people who just say, "But Tag, I'm in your class just because I'm curious about this stuff. I'm a retiree. I'm living on my retirement money. I don't really need to find a job." Well, in that case, all I just said in the last 15 minutes does not apply to you. But I look at this audience here, I do not see someone who is likely to be a retiree. Tech, are you saying that a 19-year-old or a 25-year-old cannot be a billionaire and just ready to retire? No, no, I mean, it's just very unlikely that they would come to American River College. Just saying. All right. So now we're going to move on back to our first topic. So I hope some of you had time to read the material ahead of time. So it's all the way back to the top. Oh, a little bit too much. There we go. Physical states, truth, numbers, and computers. If you want to succeed in my classes, I think it is important to read the notes ahead of time. In other words, all of these are things that you have to read. You will eventually get to all of them, and in the order that they are listed. So that means if you have time and you go like, I really want to get a good grade in this class, so that I can understand the material. So by the time I'm in a job interview, I can answer those questions. Then I think it helps to read ahead of time. Okay. Now, does that mean that people actually read ahead of time? Probably no. Maybe a few people would read ahead of time. And I can tell you that as a student myself, 30 years ago, I do not read ahead of time. But I am different from most people because I'm driven by curiosity. If I read something ahead of time, it just kills the curiosity part. Whereas if I don't know what the teacher is going to teach on that day, I walk into the classroom, energized, and go like, okay, teacher, please tell me what you're going to teach today because I'm really excited to learn new stuff with a facial expression like this. That would be me. But from many people, I'm not the norm. Okay, so that means if you're closer to the norm, you probably want to read ahead of time. It is important. All right, so we are going to get into this. And based on my experience yesterday with the Monday, Wednesday class, I am going to skip a few things. I will kind of give you a general idea of what they are, but I'm not going to get into the details of that. So, computers are physical devices. In other words, they're not magical devices. They're electromechanical devices. They actually have real components and they have a physical presence. So, that means everything that we do in programs has some kind of a physical manifestation. Does that make sense? Okay? So, what we are doing in this class, I can give you a map of this class also, is this class is bottom up. As much as you have heard about the benefits of a top-down design, top-down software engineering, this class is exactly the opposite. The way I do this class is I introduce transistors first. What are transistors? So I'm skipping to the transistor section here. Okay, so all the previous one is not so that important. What are transistors? I mean, you guys can, there's no answer here. There's no wrong answer here. So go ahead and give me an idea of what you think a transistor is. Yep.
It's a controller for electrical signal.
It is a controller for electrical signal. So it does something with electrical signal, yes. And in fact, It is a very simple device. It's a switch. That is basically what a transistor is. It is a switch, just like a wall switch that you see here. And these are complicated. It's just a wall switch. You can turn something on. You can turn something off. That's it. That's what one transistor can do. You go like, that doesn't sound like something that can do all the complicated things like Chat GPT. So what do you think makes it possible for transistors to implement complicated systems like Chat GPT, like your Canvas system, and so on and so forth? What do you think? Each transistor is only a switch. So what makes it possible to do all the fantastic stuff that we can now do with computers and cell phones too? I mean, your cell phone is not really a phone. Your cell phone is a computer pretending to be a phone, and it's doing a very poor job pretending to. So, what makes it possible? Massive number of transistors. How massive are we talking about? How many transistors do you think you can find on a i5 processor that's on your computer that you bought last year? So, i5 is not even top of the line, right? I mean, that's kind of like middle of the line, not quite at the bottom, but not quite at the top either. So how many transistors do you think is on the die, which is the silicon portion, the actual size of the processor? How many do you think is there? You can do a Google search. I don't, this is a class where I don't think knowledge is something that you should know like right off the bat or be able to memorize, because you can look it up. So let's look it up, okay? So we'll just say transistors and i5, and this is from Quora, and it's from 2017, so it's not really quite up to date. So let's see if we can find something that's more up to date. Tom's Hardware. Okay, we'll put a year limit here as well. So we want to look for something from 2022, last year. All right. So right there. All right, so we have. Oh, I thought there's an i5 is a Ryzen 5. So i7 has. No, that cannot be right. I mean, I'm not sure what unit they're using. I think they're in trillions now. Okay, so these numbers do not seem to be making any sense to me. Okay, let's click on this one. There we go. Okay, so in 2020, okay, it's not even 2022. Most processors have 2.6 trillion transistors. What is a trillion? What does it mean when we say trillion? How many people are on Earth right now? We just broke a certain landmark. So how many people do we have on Earth? 8 billion or so, right? So how does a billion relate to a trillion? A trillion is 1,000 billion. Okay? So 2.6 trillion means for each person on Earth, okay, you will be holding 300 transistors. And when you add all the transistors from every person on Earth, then you have all the transistors in one single processor. And we are not even talking about a mainframe processor or some high power processor. We are talking about a run of the mill kind of processor on the laptop computer in 2020. How many people know of the Moore's Law? At least heard of it. Okay, some people are nodding, saying yes. So the Moore's law basically say the number of transistors, the density of transistors will double every 18 months. Or that's kind of the projected trajectory. So that means in 2023, we are looking at probably something way more than 2.6 trillion transistors per chip. So it is the number of these things that make computers possible. Okay. So getting back to this class. So what are we going to do in this class? We start with transistors. Okay, we'll talk about transistors a little bit, and then we'll make things out of transistors, and we'll make things out of the thing that we made out of transistors, and then we'll make things made out of things made out of things made out of transistors, and so on. So we are building from the bottom up to the concept of a processor. I'll get to you later. And then from there, we'll start to say, okay, now that we have a very simple processor with memory and whatnot, what do we do with it? We program it. But what kind of programs are we going to write on that thing? We're going to write fun algorithms, okay? We're going to write the algorithm to solve the Tower of Hanoi, the recursive implementation of Fibonacci, and all those fun stuff with that processor. That processor will have 256 bytes of RAM. You heard me right. 256 bytes. One byte has 8 bits, and that's it. And you'll be implementing these algorithms on that little processor. Go ahead.
Um, just going back on the transistors thing, there's, and then relating it to us people, there's 86 billion neurons in our brain. So,
Mhm. So the brain is also very different compared to computers because one neuron actually does a lot of processing. Because a single neuron, the information that is stored in our brain, at least as far as we understand at this point, has to do with the synapses. In other words, when a neuron connects to another neuron, each connection stores a little bit of information, and that information is not binary either; it is analog. So the human brain is actually far more complex than a processor that has the same number of transistors because the way we do processing is entirely different, and the way we store information is also entirely different. So a trillion or 8 trillion neurons is going to be far more complex compared to 8 trillions of transistors. So that's a very good fact that you just disclosed. It's kind of interesting. All right, so that's kind of the map of this class. Okay, we build things from the ground up, and yesterday, a few students asked questions, which are really excellent questions. One question is, I don't understand why I need this class. I don't understand why this class is in the program. Why do I need this class to get a computer science degree? Okay, so I'm going to open it up to you guys, okay, because I want you to think. I don't want to give you the answer. I want you guys to think, and then we'll talk about it. So, why do you think this class is in the program? Yep, go ahead.
I can see it being helpful understanding how the hardware we're using is built and the design philosophies behind it.
hmm Because if you want to be a computer engineer or if you want to be an electrical engineer, the people who actually design and implement the processors, the GPUs, and the programming of the FPGA on your cell phones, if you're interested, I can explain all of those terms. But if you want to be a part of the teams to design the hardware, you need to understand all this stuff anyway. Okay? So some other people say, but I just want to write programs. I want to be a game programmer. I just want to write programs. Why do I need to understand all of this stuff here in this class? So what do you think is related to programming? People who are only interested in programming, this class is still of value. What kind of value is that? It has to do with how memory is utilized in a C or C++ program. Everything is stack based, including the local variables and whatnot. So if you write programs right the first time, you never have bugs of whatsoever in your programs. I'm sorry, this class will offer you nothing helpful in your programming. So does anyone want to let me know that, yeah, I've written programs right the first time, every single time, and I think in the future I'll do the same thing. I'll be the first one to say, oh, whenever I write programs, I make all kinds of mistakes. I have all kinds of bugs. The question is not whether when you write programs you have bugs or not. The question is How quickly can you catch those bugs? And I can catch my bugs really, really fast because there are certain techniques. But I'll tell you one thing, you can write a C program and you can write a bug or a flaw in the program where the behavior of the program cannot be explained unless you have taken this class. In other words, if you want to be a developer and you're writing programs in C and C++, possibly some other languages too, but I'm not 100% sure. But for C and C++, you can potentially write a program in a way that the flaw will give you a symptom that you cannot possibly explain using only concepts that you have learned in C and C++. I don't care how much you know about C and C++, about the standards, you would not know what went wrong with the program. But after taking this class, you will have some idea. It's like, that is a really, really strange, symptom that I'm looking at. I think it has to do with something like that. Then you know what to look for. It will give you a chance of catching that bug. Okay, so that really is the practical value of this class, and not just this is in the program for all the 4-year university. I have to take it anyway. Might as well take it here to save a few bucks. Okay, that's a pragmatic consideration. I understand it, but there are also far more, much more far-reaching, reasons why this class is actually important. All right, so now we can actually go in to talk about this stuff here. So transistors are switches. So instead of doing, talking about all the other stuff here, I am going to start something else. So I'm going to start logisim, which is a program that you'll be using. You do have a lab today. Yesterday, in yesterday's class, some people, for whatever strange reason, decided not to stay with the lab. So they did not do the lab until like 10 p.m. They asked me, it's like, oh, I didn't do the lab today. What should I do? Well, do better on Wednesday. That was the reply. Well, not in exactly those words, but that was the message. All right, so I'm going to show you. Um, Actually, I changed my mind. I'm going to take row first. So the way I take row in this class is I just get a activity like this, and then I just change the date to today's date. So I will put it here. You can't see it yet, but you might want to sign in to Canvas on a mobile device or on the computer in front of you right now. So by the time you're in, you'll probably be in time to participate in the row taking activity. So the way I take row is just doing something like this. I just make a quote unquote quiz that you can participate in. And the quiz is going to have a access code. So the access code, I will write it on the whiteboard just so that you guys can see it when I move on to something else. And I'll do it on 2 spots, just so that people from both sides of the classroom can see PN, lowercase, is the access code for row taking today. And I'm going to assume that people can get it done within, 15 minutes? So that will put us to 9:50. Okay, so 9:50 a.m., 9:50, 9:50 a.m. And then, the activity itself, the question is really simple. It just asks you, I am present today, is either true or false. So for people who answer true, yes, I will count you in as being present today. For people who are not here, which means it is not applicable unless they watched the video, I'm sorry, you just missed today, and it is counted as an absent. For people who intentionally answer false, I'll count it as 2 absences. No, I'm just kidding you. So save and publish. Now you can refresh your browser or your app. You should be able to get to this row taking activity. It is right below the transistor topic, and the access code is PN. So if anyone has trouble getting that, let me know. Are we good? Can someone confirm that you can get to it? All right, excellent. Thank you. Because sometimes I make stupid mistakes and go like, ah, man, that doesn't work. Usually the wrong date. All right, excellent. So when most people are done, we're gonna move on. Okay. So that's one thing you can do. When you get to this classroom, is just sign in. If you want to use the workstation in front of you, that's fine. If you want to bring your own devices, that works too. Okay. So either way is fine. So the first thing is to sign in, and it really helps to sign into the computer because then you can open up your own browser to stay at a certain place of whatever I'm talking about. So when I scroll around and you're feeling nauseated, you can just kind of look at your own screen and go like, okay, now I'm not getting so nauseated. I'm not getting the motion sickness from text scrolling around in his text. Are we good so far? Is anyone having problem getting in to participate in the road taking activity? You're still having some issues? Oh, if you're on waitlist, you should still be able to sign in because I put all the waitlist people into the class too. So you should be able to sign in, but if not, just write your name and your student ID on a piece of paper and let me have it. Then I'll count that as your road. Yeah, but you still want to be able to do the lab, so it's important that you try to sign in. If you cannot sign in, let me know and I can add you to the wait list of in-campus. So we'll do that after the lecture. Okay, all righty. Okay, so now that we got signing done, we are going to look into logisim. And logisim is a tool that we'll be using in this class all the way to the end. Oh, no, I don't want to display the clock. I want my terminal. Okay, there we go. So I'm using Linux. If you're using Windows or Mac OS, the instruction is going to be a little bit different. There are links within the lab itself to bring you to the instruction. If you're using Windows, how do I get around the file system? If I'm using Mac OS, it's about the same as Linux, but there are a few other considerations. So I use the command line a lot in this class. Okay, and I'm hoping that most of you will get comfortable with the command line by the time we get to the end of the semester. All right, so the way I do this is I use java-jar, and then I have a path to the jar file, which is sitting in my home folder. So in Mac OS and also in Linux, the tilde symbol is a representation of what we call the home folder. In Windows, it's a lot more cumbersome, but they also have a concept of a home folder. And then I have in documents, CISP 310, processor, and then finally the jar file. Okay, so in the lab today, you will have instructions of where to get the jar file and what to do with the jar file. So don't be concerned that you have no idea how to do all this stuff because there are instructions in the lab today. And you have 1 hour and 20 minutes to do the lab, which should be sufficient. The key to do the lab is to read carefully. Okay, all the instructions are in the lab itself already, so do not just skip over stuff and think that, oh, I know how to do this. Make sure you read the instructions carefully. So that starts up logisim on my other screen, which I will move to the screen that you're looking at. Nope, it did not do that. Let me try that one more time. There we go. All right, so this is logisim. Logisim, as the name implies, is a logic simulator. So we build circuits in this particular tool, and then it can simulate the running of the tool of the circuit, and then we can figure out what to do and how to get how to design circuits and how to test certain types of circuits. By week 8 or so, week 8 or 9, you will start to use the processor. And guess what? The processor is just a gigantic circuit. That is the processor. This is what we are writing the programs on. It is not an Intel processor. If you ever talk to some of your peers, taking the same class but in a different campus, they will all be telling you, "Oh, we're using the Intel x86 processor." Okay, the instruction set is blah 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 like that. No, we are doing something entirely different. This processor you cannot find commercially. You can find very little information on the internet for this one because it is called text toy processor, TTP. Okay, so why do I do this? Because I want you to see what is inside the processor and how it works. Okay, but that's week 8. Okay, but what we'll do today is not using this processor. We are building the smallest building block of a computer. We are building what we call a gate. A gate is nothing more than an operator. I hope you guys do remember what is ampersand ampersand in C++. What is that? Can someone tell me what is? Yes, go ahead. It is a logical AND operator. So a gate is just like an operator, except it doesn't look like an operator. Okay, you have to use wires to connect to the input, meaning the left hand side and the right hand side, and then the result of the operator has another terminal and go like, okay, hook up to this terminal of this device to get the result of the operation. So they are basically the physical equivalents of a logical operator. Okay, so we'll get to the wiring stuff later. So what I'll do is I am going to first introduce so this part here is like a catalog of types or classes in programming. In other words, we are looking at what kind of components can we put into the circuit. Each one of these is a class or it is a type. Are we familiar with the concept of type or class, coming from CISP 360 or object-oriented programming? We comfortable with that? Int is a type, unsigned is a type, char is a type. Are we good so far? All right. So now we can pick up some of these things and go like, yeah, I need one of these or two of those and so on. So I need power. Okay, so power is basically the source of ones. So just look at this as the infinite source of one. Okay, whatever connects to the power get one. Okay, as the connection. And then the opposite is ground, which is the infinite source of zeros. So if you want to zoom in this particular tool, it's a little bit cumbersome. You go to the bottom left, and then you click this, to kind of control the zoom ratio. Okay, so it's not like just using the wheel of your mouse to zoom in and zoom out. This is a pretty old program, and I had to go to the source code to make a few amendments, to get it to work. So it's a little bit cumbersome, but it does work. Okay, so now we finally get to transistors, like here. So I'll just pull one transistor to talk about it, and then we'll get the circuit going. Okay, so this is what a transistor looks like as a symbol. In this class, we are not going to talk about what is inside a transistor, what makes it work, and so on, which is fascinating. Okay, this is also what we call a MOSFET. MOSFET, MOSFET, stands for metal oxide semiconductor field effect transistor. Every single word has a very specific meaning, but we are not going to get into that. We'll just look at this thing and go like, it's a switch. So like every single switch, you have a lever, right? You have a lever that is used for controlling, am I turning on or am I turning off something? Does that make sense? That lever to control your on off is right here. That is called the gate of a transistor. Are we good so far? Some of you look really bored. That's probably because you read this entire article or whatever I wrote, ahead of time. You go like, yeah, I read it already. I know all this stuff already. So let's hope that is the case. So this is called the gate. Okay, it is the control of whether I want to turn on or turn off the device. Okay, so what do you think the other two terminals or the other two what we call ports are representing? This one and this one over here. If you have a switch, like a wall switch, electrical switch, what other things do you need?
Input and output.
Input and output, right? So is the input connected to the output? That is the question. The job of a switch is sometimes we want the input to connect to the output, and other times, no, we don't want the input to connect to the output. So very good. I have not thought of the term input and output because I always overcomplicate things. So the input, so just looking at the symbol, which one do you think is the input and which one do you think is the output? Go
The
ahead.
left is the input, the right is the output.
And what makes you think that?
The arrow in the switch.
Exactly. Very good. So you're making use of the information as much as you can, because without the arrow, it's really hard to say which one is which one. The arrow is telling you it is going from the left to the right. So the left is the source, and the left is called the drain. The source is also the input. The drain is also the output. So let me just point to the device because this is going to be recorded. This is the input, this is the output, and this controls whether the output connects to the input or not. Are we good so far? All right. So now that we know the anatomy of a switch, the next question is, so how do we turn this thing on? And by the way, what do we use as the input, and what do we use to control the flow of the switch? Zeros and ones. Okay, we're going to make everything really easy. It's all 0 and 1. 0 can also be interpreted as false, and 1 can also be interpreted as true. Is that okay so far? So in this class, 0 and false are kind of the same thing, and then 1 and true are kind of the same thing. Is that okay? All right. So now the question is, how do I turn this on? And by the way, if I did not take notes whatsoever today, which I do not see a lot of you doing, how do I get this information back? Do I really have to watch the entire video recording of the lecture to get all this stuff here? Absolutely not. Okay, because logisim comes with its own help. Yeah, right here, help. But it's not an AI. You cannot just ask a question. You cannot just type, tell me what is a transistor or where's the input of a transistor. You kind of have to do things the old school way. You go to library reference, and let me bring the window up here, like that, okay? And you can see the structure of the categories are exactly the same over here. So that means, where do you think that I would find transistors? In the which category? Wiring. Very good. Okay, so you guys are recognizing the pattern here, which is important. Okay, so you go to wiring, and then you go to transistor, and it's exactly at the same place too. So the ordering of the categorization in the help menu is matching exactly the way it is here, in the tray that tells you what kind of components you have in logisim. So you get to transistor, and this is a pretty long discussion of a transistor. And this is a truth table, okay? So let's go ahead and talk about the truth table a little bit here. So in the truth table, we are looking at, summarized form is better. So we're going to focus on just the summarized form, which is right here. All right. So to read this carefully, you have to be careful because gate is not referring to the left-hand side, and then drain is not referring to the right-hand side. The caption here, gate, is only for the truth table, and then drain is only for the truth table. So gate and drain are not labels for the diagram. They are labels for the table. They're labels for the table. Are we good so far? Okay, sort of, maybe. Okay, I see some frowning. Okay, so what that means is gate is referring to this column of the table. Drain is referring to this column of the table. But what does it mean? Well, it means when the gate is a 0, the drain connects to the source. In other words, the device is quote unquote turned on because we have connectivity between the input and the output. In short, to turn on a P-type transistor, the gate should be a 0. Are we good so far? Okay. What about the 1? So this is for p-type transistors. If the gate is a 1, we have a Z here. What does a Z mean? Z means it is not connected. That's all Z means. It's sleeping. Okay, that's an easy way to remember it. Z means it is sleeping, not paying attention, not connected to anything. It's just the electrical engineering term. It is what we call floating. Is that okay? All right. So now we take a look at an N-type transistor, which is right here on the other side. Do you see that the 0, 1 versus what they do is exactly the opposite for an N-type transistor? So an N-type transistor, when the gate is a 0, the device is off. Okay, the drain does not connect to anything. But when the gate is a 1, then the source connects to the drain, which means we have connectivity and the device or the switch is on. All right, so I'm going to pause a little bit here and see if there are any questions regarding the truth tables for a p-type transistor and an n-type transistor. Do we know how to read this table? Yep.
So the gate and drain on, on the table, that's the states of the gate and the drain under specific.
All right, so the drain is labeling the column to basically say how is the drain connected.
Right.
So with the source here, it means the drain is connected to the source when the gate is a 0, which means the device is on because you have connectivity. You just flip the switch, and there's contact within the switch to connect the input to the output.
Right. I was asking if the truth table corresponds to the states on the transistor itself.
Yes.
Okay.
Yep. The truth table is describing how to make use of a transistor. How do I turn it on? How do I turn it off? That's what the truth table is trying to tell you. All right, so I just mentioned there are 2 types of transistors. One is called P and one is the one called N, and hence PN as the passcode of your rotating activity. Okay, so the next question is, how do I differentiate a P-type transistor from an N-type transistor? Just looking at this diagram, can someone tell me, what the differences are? I can tell you right away, it's not about the colors. Okay, so ignoring the colors, what is giving away what type of a transistor we are looking at? Yes.
Active when it's on.
That is true, but from just the symbol, how can we tell?
The circle.
The circle, very good. Okay, that is good observation because only a p-type transistor has a tiny little circle here, which may be difficult for people in the back to see. Okay, but there's a little bubble here for the p-type transistor, and there's none for the n-type transistor. All right. So I'm going to digress a little bit again. I'm going to tell you, what I think may be useful when you're taking notes. Definitions, okay? So you want in your notebook, okay, whether it's electronic or not, I would dedicate a few pages on just definitions, what things are, okay? In other words, right now, I'll be drawing an N-type transistor without the bubble and say this is an N-type transistor. And I would be drawing another transistor with the bubble and say this is a P-type transistor. That's what I would be doing because the exams of this class does not test you for knowledge. In other words, there are no point values whatsoever for knowledge because the exams are open book and open notes. You can always look it up. So what do you think I'm going to test you on? This has to do with the syllabus too. That's why I'm indirectly testing to see whether you guys actually read the syllabus. So what do you think the point values are associated with in the exams for this class? If I don't care whether you know stuff or not, because it's open book and open notes, you can always look it up. What do you think I'm going to testing you on? Yes.
Understanding and implementation of the material.
Okay, understanding of the material, very good. But how can I tell whether you are understanding the material or not? Do you think I would come to you with a Vulcan mind meld to read your mind to see whether you actually understand the material or not? Okay, some of you do not have no idea what I'm talking about. Some of you are laughing because you know what Star Trek is. Okay. Long story short, I cannot tell what is on your mind. I cannot really tell whether you understand something. What I can do is to give you a problem to solve. Okay? So how do you solve a problem? I say, okay, implement a circuit to do X, Y, and Z. Okay? How do you do that? But first of all, you have to understand the question. Most people skip that part, which I really cannot understand because if people do not know what the question is asking for, what are you writing down? So understanding the question is a matter of connecting the question itself to concepts that you have learned already. It is a analysis. Okay, you're looking at the question. It's like, okay, so the question is asking me to make a circuit to do this. What exactly is that referring to? Okay, do I understand all of those terms? Can I find the definitions of those terms? The question may also say only use AND gates, OR gates, and NOT gates. Do I know what is an AND gate? Do I know what is an OR gate? Do I know what is a NOT gate? So that is the first part of answering a question, that requires you to implement something to problem solve. That part will give me some idea of whether you understand the material or not. But that part is not being able to connect the question to things that you have learned already is only a small portion of what I'm testing. Because the other portion is can you apply what you have learned dynamically to give me the solution? Now, when I say dynamically, means the process of doing that may not be something that I have talked about in class. I'm not testing rote learning. I'm not testing whether you can follow a process sequentially, step by step. I'm testing whether you can make those connections on the fly dynamically to connect things together to make a solution, to give me the solution. So those two steps, okay, one is analysis to break down the question, to understand what it's asking, to understand how it connects to the concepts and the techniques that we have talked about in this class is one part. The second part is called problem solving, and that has to do with applying what you have learned to come up with the solution. That is what the exams will be asking. Is that okay so far? All right. And I do not teach to the exam. I know a lot of high schools do that. The teachers will teach to the exam because they want the high school to look good. Okay, you guys are not responding to that one because you might have graduated from high school just recently. So that stuff has not sunk in yet. But a lot of times, okay, high school teachers want to make sure the high school looks good, so they put in a lot of effort to make sure that you score well in the exams. But sometimes by doing that, they are neglecting to make sure that you understand the material. So I want you guys to understand the material much more so than making myself look good and say, hey, look at my grade distribution here. Most of my students got A's. I don't really shoot for that. Okay? But I do want you guys to understand how to gain knowledge and how to apply your knowledge. All right. So I just want to kind of disclose all of this stuff here, just kind of gradually. So this way you understand, how to prepare for the exams. So one more thing, it's not a digression per se. So knowing all of this stuff here, do you think you can do stuff like every single time you're in the lecture, every single time you're doing the lab, and every single time you are doing something with this class? Do you think you can do something incrementally to prepare for the exams? Or do you think you just wait until a week before the exam and then just do one huge, gigantic, one-day thing to prepare for the exam? Spread it out, okay? You already know it is open book and open notes. You already know it is always going to be on paper, no electronic devices in the exam. So what do you do every single class?
Take notes.
Take notes, because that is going to turn into your
Study guide.
huh?
Study guide.
Study guide. Thank you. That's exactly the phrase I was looking for. That's going to become your own study guide. I do not give you a study guide. Study guide is something that you create or develop for yourself. If I give you a study guide that would work for me when I was a student, I would say 90% of this class would not find it useful. So you have to create your own study guide, but you don't do that just a week before the exam. You do it constantly. Every single time I introduce something like this, you add that thing, the definition, the description, to your own study guide. You can do it in class right now, which is good. You can do it right after class. But it's a gradual process that you have to spend time to do. It's not something, once again, that you do in 2 hours a week before the exam. That would not be a good use of your time. Okay, so now we got this. I'm just looking at the time because I do want to show you how to use logisim a little bit. So now we got to create a circuit. So I would do this, in a relatively fast way. I need two of these things. And the first thing is I need to rotate it. Okay, it's not in the right orientation. So once you select something, you would also notice that the properties of that something is displayed here, and they can all be changed. So you can change the type, you can change the orientation, which way it's facing, meaning rotation. You can change the left-right thing, which is a mirror image kind of thing. And this one we are not going to touch just yet. Okay, so keep it at one single data bit. So I wanted to point down. I want the arrow to point down, so I have to change the rotation. So instead of facing east, I need it to face south, like so. And then I make a copy of this. To make a copy, you can always just kind of replicate the whole process, but the shortcut to do this is to go to Edit and say Duplicate. Or you can type Control D on the keyboard. It's the shortcut key for doing that. So you select whatever you want to duplicate. It can be a selection of things, and then you type Control D, then you get a copy. And then you move the copy somewhere else. Okay, so I'm gonna move this over here. But this one, I wanted to have a mirror image. Can someone remind me, how do I do a mirror image? Yep, change the gate location. I don't want it to be on the left. I want it to be on the right, like so. Okay. And I need two N-type transistors. Since I got two transistors here already, I'll just do another duplicate, Control D, and move the selection somewhere else. But I need both of these to be N-type transistors. What do I do now? Change the type. And the best thing is you can actually change the type of both at the same time. If it shows up here, together, you can change both together, like so. So now they're both N-type transistors. And I also do not like the orientation. I want these guys to be pointing up. What do I change? If I want to rotate it 180 degrees, what do I need to change and how do I change it? Hmm? Yep, change the facing from south to north. That is correct. So now it's just a matter of just moving things around to make it look nice. Okay, so we'll move this one kind of over here. We'll move this one kind of over here. And then these two, one can be here, and I might need a little bit more space. And then move this one over here. Okay. So now I got all the components kind of spaced out correctly. It's time to make connections between the components. You also need to pay attention here because you can only make connections when there's a little bubble. Okay? In other words, these points here, making a wire from here to somewhere else doesn't do any good. So you need to go from where a bubble appears when you just kind of hover over that point to another point that also has a bubble. Connecting to any other place is not functional whatsoever. Okay? So I need to make sure that I go from here to, oh, okay. You can also make a wire not connect to anything and then continue the wire from here. So these are all drag operations. You keep your mouse button down and just drag it. And this one, I kind of needed to go all the way here, make a connection here. And then here, I make a connection here. See that big dot over here? It is also significant because the big dot means, oh, these three wires are actually connected. Okay, so that means sometimes they're not connected. I'll show you what that situation in just a little bit. This connects here. Drag. Okay, my mouse is. There we go. Nope. Okay, one more time. There we go. And then there we go. And then we have, oh, I forgot two more things. This is an input pin. We need two of those. So as I said a little bit earlier, we can always control D to duplicate. And we need one output pin. And I can grab it from there and I'll stash it about here. Do we have any questions about, how I did all of these things? Are there any specific steps that you want me to kind of go over again? Okay, so it's fairly intuitive. It's a little clumsy, but other than that, it's fairly intuitive. So I want to connect this one to this one over here, and also connect this one over here. All right, so now we have a little bit of an issue, and there are multiple solutions. I want to connect this one to this one over here. So I'm going to take it like this, and this is this is not going to work. Oh, okay. Well, I can change the design a little bit. I will select a bunch of components, and I'll just drag the entire thing down a little bit like so. And this looks kind of ugly, so I can drag the entire segment, just drag, and drop. All right, so now I can actually illustrate what I want to say. So now I'm going to cross over here. Okay, so the question is, do you think I just made a connection to the vertical line, or do you think I did not make a connection to the vertical line? I did not make a vertical line because you cannot see a big dot over here. So the big dot is significant because it tells you whether you have a crossover like this one, or flyover, versus we actually have a junction. All right, so we want to make this connect here, and this end to connect here. And then we have this thing to connect to here. All right, so now we have a gate, okay? So the question is, let me turn off simulation first and then reset the simulation because I don't want the colors to kind of confuse you about what is going to happen here. But I do want to show you what I want to experiment first. So let's say one input is a 1, the other input is a 0. What do you think is the output? In other words, knowing that the top input pin is a 1, the bottom input pin is a 0, what do you think is the output, which is the little circle thing on the right-hand side? But Tech, you haven't really talked about this. You haven't talked about the circuit. That is true, but I did talk about the transistors, didn't I? So the question now is, can you apply what you have just learned about the transistors to find out what the output pin should be? It's either a 1 or a 0. So how do you figure that out? What is your thought process? Now, I'm not expecting you to do that like really fast, like the way that I can do it, because I have been teaching this class for a long time. But I'm asking, given time, how do you do that? Yes?
Figure out which gates are open, which gates are closed, and which signal is the output.
Exactly. So you want to find out what are the states of the transistors, right? Do you want to find out, is this transistor connecting the input to the output? Is this transistor connecting? And so on. So let's analyze all of that, okay? Second question, did I talk about that? Did I talk about how to determine whether a transistor is connecting or not? I hope the answer is yes. Okay, I see a little bit of nodding, but a lot of I would say floating responses, which means it's not one way nor the other. So I hope the answer is yes. Okay, I recall that you talked about it. Now, can you remember what it was? Hmm, if your answer is no, I cannot remember, then I'm gonna say, did you write it down? Or do you know where to find the answer? Because do I expect you guys to remember everything that I say? The answer is no. Okay, that would be unreasonable. But then if I ask, do you know where to find that information? If the answer is no, I would start to worry. If the answer is yes, I can find it in the help, with built into logisim, great, okay? Or yeah, I wrote it down, on one of the pages of my notes and I can go back and find it, even better, okay? But if the answer is no, I have no idea how to find that piece of information, I would worry, okay? So that kind of tells you, and I think this approach is appropriate for every single class that you are taking. All right, so we'll analyze the transistors one by one. Okay, so I'm going to point to the transistor here, and I'll ask you, is this transistor connecting? How do you know whether whether this transistor is connecting or not? Yes.
The input going to it,
The input connecting to it is a
one.
one. Very good.
What
And
on a P transistor means
it is off, right? Okay, very good. So we have to identify a few things. One is what is connecting to the gate. That should be easy. Follow the line until you get to an input pin. Okay? Second thing is to identify, is this a P transistor or an N transistor? How do we differentiate? The bubble, okay, the little circle, it is here, it is a P transistor. So given this is a P transistor and the gate is a 1, does it mean it's on, connecting, or does it mean it's off, it is not connecting? Look up the table, okay? Do we know where to find the table? I hope so. Or some of you might have written it on your notes too, so that makes it easier to find the information. So we know this one is not connecting. It is as if the entire transistor is not even here. Okay? What about this guy here? Is this transistor connecting or not? It is connecting. Yes, go ahead. It's connecting because the gate connects to 0. And what type of a transistor is this? It's a P transistor. And with a P transistor, the gate is 0. It is connecting the input to the output. Okay, very good. What about the other two transistors down here? What about this guy over here? Is it connecting? What type of transistor is this? Is an N type transistor because it doesn't have the bubble. And what is the gate connecting to for the transistor that I have just highlighted? 0. So is it connecting or not? It is not connecting. Very good. And what about the last one down here? This one is connecting. So I just realized when I ask you, what type of transistor it is, you just read it off the screen. So that was a stupid question to ask. All right. Okay, so now what happens? Okay, so this transistor is, this one is on, this one is off, this one is off, and this one is on. So let me show you, basically what it means, okay? It is as if this thing is not here. It is as if this thing is not here. And the remaining transistor are both connecting. So now the question is, what do you think the output pin is connected to? I'll give you three choices. It is not connected to 1 nor 0, power or ground. It is connected to power, which means it is a 1. It is connected to ground, which means it is a 0. So of the three choices that I just gave you, which one is it? And how do you find that answer? You follow the line, right? So let's follow the line here. So you start with the output pin, and then you go to this junction here and you go like, well, I can go up or I can go down. So let's go up first. So you go up and you go like, well, is there a way for me to connect to the source of all the ones? What do you think? Yep, because this transistor is connecting, so that means I can find the path to the one. Okay, what if I were to make a decision to go south, to go down? I go down and go like, that's it. Even though this is connecting to ground, there's no way to cross this gap here. So that means the output pin only has one way to connect to one, no way to connect to zero. So what do you think the output is? It's a one. Very good. So by repeating this exercise, okay, so let me undo the two steps here. So by repeating this exercise, I can find out a few things. So if I go back and turn on simulation again, so if the input has at least one zero, I don't care which one is a zero, if it has at least one zero, the output is going to be a one. Because that means I have at least one path to connect to the one and no path to connect to the zero. It is only when both inputs are ones that I will find a path to connect to the zero and no path to connect to the one. So I just claim a few things and logisim agrees with it. So what are you going to do? Are you just going to sit in here and go like, yeah, if text says so and logisim agrees, I'll just state it as a fact? Or are you going to question it and go like, okay, that seems to be true, but why is it like that? Which way are you going to go? I'm not going to give you the answer, but I would just say that, I just gave you three exercises for you to do. Because for each of those scenarios that I did not go into detail to analyze for you, you should try the analysis yourself and verify that you understand why in each one of those scenarios the output is a zero, and this one is a one, or the other way around. I think it's one, and a zero. So I just gave you three exercises. Okay, it's sort of hidden, but this is the kind of stuff that you want to be able to do for every single class, is to create your own practice exercises. When your professor, there's only so much time in a lecture. I can only cover so much material. So when I state something as a matter of fact, you can question it. You can go like, okay, the professor said that, the tool even shows that is the case, but do I understand why that is the case? You just gave yourself a chance to practice. And the more practice you do by yourself, the more familiar you are with the material. But not only that, it also means the more your mind is ready to tackle problems that you have not seen before. So this kind of exercise will help you not only in this class, but in basically all the STEM classes that you will have to take, especially at a four-year university. So I'm trying to give you the tools to get you guys ready for a four-year university, not only to be successful, but also to get as much out of it as possible. All right, so what we'll do next, okay, we are running out of time for the lecture, so I will show you a few things that you may find useful. So the first thing is for me to get back to the browser right here. So if you go to YouTube and you go to my channel, which is some profs, some professors, you will find this page. And then what you do is you go to videos, and it will basically list all the lecture recordings in a reversed chronological order. This is from yesterday. So I'm going to upload the lecture recording for this class, which is still being recorded right now, between the gap of the lecture and the lab. So it may not be ready yet by the time you start your lab, but it should be about ready by the time you start your lab, which means if you bring your own headset, Bluetooth or whatever, because you can access it on your phone as well, you can actually listen to the lecture while you are doing the lab. Now, is that going to be helpful? I don't know. I mean, it's just something that is going to be available to you. And this is public. You don't need a password. I never take down my lecture recording whatsoever. So you have access to the lecture recording for the entire semester. For those of you who want to say, but I really want to know what you're going to teach on Wednesday, or in this class, Thursday, you can actually go back to the last semester and actually pre watch what I will be teaching. You can time travel in this class. And guess what? You have multiple destinations as well because I have kept lecture recordings since 2011. That is a lot of semesters. And I keep every single one on YouTube. So if you say, I want to watch the, the lecture from 4 years ago, you can dig it up because the lectures are time stamped year, month, day. So you can quite easily correspond to whatever calendar is in that particular semester and find out, oh, this is the second class or this is the fourth class, and you can pre-watch what I will be teaching. For those of you who go like, okay, I don't want to read because it's a lot of stuff. I just want to listen to what you have to say. You can do that. All right. So one more thing before we take a short break, because I know you guys are thinking, this is draining. I need a break. I don't blame you, but I'm not going to change anything either because there is a lot of material for this class. All right, so this is what you need to do. I will fix the time and whatnot. So it is in the form of a quiz, and you can retry as many times as you want. So it allows multiple attempts. It keeps the highest score, which I think is friendly. But this is what you want to write down. Okay, logisim is the access code. I will write it on the whiteboard. So we have lowercase logisim as the access code of the lab. So, and I will make it due at the end time of the lab, which is about noontime, I think. So 11:50 is the end time. There we go. Save and publish. All right, so that's one. There's one more. Okay, so do not forget about the second one. So after you complete the instructions of the lab, you will have created a file. So once you have created the file, this is where you upload it. So it also contains instructions to check whether your circuit is done correctly or not. So that part is optional. If you just say, yeah, I think I got it right, you can just go ahead and upload it. But if you get a score less than perfect, then you can say, man, what did I do wrong? Well, you could have checked it and make sure that you got it right the first time. So this is also going to have the same due date, which is 11:50 a.m. Like so, save and publish. So now you have the lab activities published, and you can access it now. You can start on it if you want to, but technically we start the lab at 10:30. So if you want to take a short break or whatever, you can go ahead. All right. Any questions before I stop the recording? Anything else that you want me to talk about that you want to be on recording? No questions like, is every lecture like this? The answer is yes. Some is going to be even more dense than what we have today. I would call today's lecture a light day. Any other questions? We all good? All right. So I'm going to stop the recorder and upload the video. You can take a short break if you want to, but if you want to jump on the lab right away, that's good too. But the lab is another way for me to take role, which means people who miss the lab they are considered absent in this class. Alrighty. So I'm gonna.
Excuse me.
So during the lab time, I am available to answer questions. So if you have any questions about the lab, just go ahead.